Okay, all right. So in the last class, we talked about all the different maneuvering models and we looked at what happens specifically for dynamic applications. How can we model the drag using a linear exponentially decreasing with speed linear drag and the quadratic drag which comes from current coefficients. Now, please understand that these current coefficients either can be determined usually using a wind tunnel experiments, or you could also get them using CFD analysis. Okay, so it does allow you for the possibility that if you didn't know anything about it and you don't have any absolute information about what those current coefficients might look like, you can always perform a CFD analysis and get those values and proceed from there. Okay? But in case if you have a sister vessels or vessels which are similar to it in some sense, you can use those coefficients in the modeling. And we primarily looked at how to include the currents into it also. So we were formulating this in terms of the relative velocity vector rather than the absolute velocity vector. The main assumption there was that the currents are irrotational in nature. So that is why we are able to make this approximation. Today we'll discuss a little bit more about where that approximation is coming from, why that irrotationality is important in the modeling of that system using relative velocity. Okay, so today our focus will be more on the left and the right hand side of the equations. So far we were looking at the inertia terms, the Coriolis matrix, the damping terms, and a little bit of hydrostatics and stiffness, which is really present only if there is a sea keeping modes there. And on the right hand side, we always had these forces which were coming due to the wind, which were coming due to the waves, and the ones which are coming due to the currents. Currents were somewhat included by taking into account the relative velocity formulation, but we didn't really talk about how to model the wind and the wave loading which is coming onto the vessel. So we'll kind of focus our efforts today on understanding what are the realistic models for wind, wave, and current. Okay, we'll first start off with wind, and you'll see that in the wind we have a similar diagram as to what we had in the case of the current. Again, here we define the wind velocity with respect to the true north, which is this angle beta VW. And then we define the direction of the wind with respect to the longitudinal axis of the ship as gamma W. And again, you see that this formulation still has that anti-clockwise orientation being positive, which we discussed about in the last class for the currents. Okay, so the same procedure still is applicable here. Okay, what we are doing here is, again, we have the same relation. This gamma W can be expressed as psi minus beta VW minus pi. Now, we can express the wind force on the vessel as half rho A times VW square times a wind coefficient. So these are wind coefficients. Times a representational area over which that force is acting. So here you'll see certain different terms come up. So AFW represents the frontal projected area. So this is the, so if I look at a hull form like this, which is floating, let's say here, and some superstructure is there, let's say something like that. Then I'm talking about this area above the waterline, which is projected onto the XY plane. Okay, that is the frontal projected wind area. Okay, and I represent that using the convention AFW. Then you have the ALW, which is the lateral projected area. So if I have the ship now like this, that's not a good ship. All right. And let's say that I have a superstructure here, There's something going here, and maybe some more equipment here. Okay. So I'm kind of looking at where the water line is, and I'm taking all the area which is coming above the water line in the XZ plane. That is the lateral projected area. So this is lateral projected area. Okay, again for the wind, we still choose the frontal projected area as the reference value. Okay, and for the roll, pitch, and yaw, you will see that there's not just an area, it will be an area times a length. Okay, so in terms of the yaw, we have seen this before. LOA represents the overall length of the vessel multiplied by the here lateral projected area. When we come to the pitch, we see the frontal projected area multiplied by a distance HFW, and that represents the centroid of the water line of the centroid above the water line of the frontal and the lateral projected area. So if in this case, let's say this marks the centroid, then this distance here is HFW. Similarly, if the centroid of this thing, let's say, lies somewhere here, then I'm looking at this distance from the water line, and that distance is HLW. Is that making sense? Yes, no?
Yes, sir.
Okay, all right. Okay, so notice here that there is one major difference, that rho A here represents the density of air and not of the water. Okay, and similarly VW here represents the wind speed. That's the wind speed. Okay, and then you have the current coefficient, the wind coefficients multiplied by the area. Okay, so let's look at what is this value of the wind density or the air density. You'll see that as the temperature changes, depending on the area of operation, you're actually seeing a significant change in the range of values of rho A. So a typical value which you will see is about 1.269 or 1.247 as some of the representational values which you will generally see in the literature. But you can see that as the temperature is increasing, the density is reducing, which is what is expected of it, because any gas, when you apply any more temperature to it or any more heat to it, it expands. So therefore it occupies the same amount of mass, now occupies more volume. So that's why the density decreases. All right. Okay, so the mean profile. So now this VW which we saw, we'll now talk a little bit more about that wind speed. Typically, wind speeds are measured at a certain height and they are standardized about that height. It is very common to see that the wind velocity is usually measured at 10 meters above the sea surface. And you'll see that that is the value which is typically used for the computation of wind loads many a times. But if I want to compute what is the wind at a different reference height, based on the idea that I know what is the value at 10 meters height, I might be able to do that using this formulation which you see here. So what we are doing is we are assuming that it has a boundary layer profile, which means that as the height decreases to 0, the wind speed is actually exactly 0 on the free surface. And then it kind of increases up till the point where it is matching with the reference wind speed at 10 meters height. And that variation is used as V10 times h over 10 to the power alpha, where this alpha is usually the 1 by 7. This is the typical power law which we assume for the boundary layer profile in fluid dynamics. So that is what we are using here to scale appropriately for any other reference height that we want to figure out. We typically are using the V10 value along with the height to compute the reference height, the reference wind speed at the height that we wanted to calculate. Okay, so these current coefficients are also generally computed using the 10-meter reference height. So, but if you want to convert them into a coefficient which refers to a different height in your formulation, you might have to look at a factor of multiplication. So typically, if I have a current coefficient at some height h2 that I want to compute, given that I know what is its value at some reference height h1, I can do that as the current coefficient at h1 times h1 by h2 to the power 2 alpha. And that h1 by h2 to the power 2 alpha is coming from nowhere but simply the ratio of the dynamic pressure due to the two different velocities at two different heights. And that ratio simply comes out to be this factor, which we are seeing as h1 by h2 to the power 2 alpha. Okay, so given that I know the wind speed at any reference height, I can compute the wind speed at any other reference height. Similarly, if I know the wind coefficients at any particular reference height, I can convert them into a wind coefficient for any other reference height which I might have, right? So the typical application might look like I may have a wind speed on my measurement on my ship using an anemometer at a certain height which may not be at 10 meters from the sea surface. In which case, I am either trying to scale the velocity back up to calculate what is V10, or I might want to compute the current coefficients in terms of my new reference height in order to calculate the wind force. Is that making sense? I can do either way. I can either convert the velocity I measure to a reference value of V10, or I can use I can try to compute the new current coefficients given that I know the current coefficient specified at a reference height of 10. Tell me this is making sense? Yes? Okay, when I'm asking that, please respond because I'm usually looking at my slide, so I don't see your face. I have to come back to see your face when you're nodding. So I can't see you nod until I actually shift my screens. So please do say something.
Yes, sir.
Yes, sir. Yes.
Okay. Okay, so typically wind speeds are characterized in terms of Beaufort scale. So we generally have a scale of range of scales and it is specified in knots. So when we have 0 to 1 knots, we call that a calm wind. When you have 2 to 3 knots, we call that a light air. 4 to 7 is light breeze. 8 to 11 is a gentle breeze. 12 to 16 is a moderate breeze. And 17 to 21 is a fresh breeze. 22 to 27 strong breeze. 28 to 33 moderate gale. 34 to 40 knots fresh gale. 41 to 48 is a strong gale. 49 to 56 is a whole gale, and then 57 to 65 is a storm, and more than 65 knots is a hurricane. Okay, so that is how we define the different levels, and these Beaufort scales are also given scale numbers. So you may typically also hear that instead of giving this specific name of what is the wind speed looking like, they may say a Beaufort scale of 7. Then you have to kind of be aware that it represents maybe some wind speed between 28 to 33 knots. Okay. So this is a very common scale which is used in the by many of the sailors, and they will be typically be communicating in this manner. Okay, you can see that a 65 knots corresponds to how much in meters per second? How much is it in meters per second?
$120.
120 meters per second. No. 1 knot is 0.5144 meters per second.
Oh, 33.
33 meters per second. Now, how much is that in kilometers per hour?
9.28.
No, 92 maybe. Check again. Missing a factor of 10 somewhere. One meter per second is the 3.6 kilometers per hour. So 33 should be roughly around
118.
118 kilometers per hour.
Right.
So those are really, really strong winds, right? And in such strong winds, one such strong wind is what wedged your Suez Canal and the Ever Given ship into the Suez Canal. Remember the incident from last year where a huge container ship got wedged inside the Suez Canal. Now they are planning to actually do more. They want to expand the width of the channel, given what the debacle happened last time. So when you have huge wind speeds and you have a large superstructure area, it becomes really important to consider those wind forces because they can be significant in trying to push you around, okay, especially along the beam, because you can't compensate for them directly. You don't have any thrusters which are working to push your ship sideways in a typical ship, right? So it's very difficult. You have to orient the ship slightly inward into the wind in order to get that so-called lift and the drag to orient it in that manner. So it is a challenging problem, and I think that was one of the reasons why Ever Given had quite a bit of a disaster there. Okay. All right. Okay, so let's see how these coefficients look like. We are mostly interested in the horizontal plane motion, so we kind of restrict ourselves to it. And then in that case, we can make a gross approximation of the surge, sway, and yaw current coefficients as a function of the angle at which the wind is coming to the longitudinal direction of the ship as some constant value Cx times cosine of gamma omega. There is a minus sign here. Similarly, for Cy, I'll have Cy times sine of gamma omega and gamma W, sorry, that's W, that's not omega. And then finally, we have the current coefficient, which is Cn times sine of 2 times gamma W. A typical value of these constants Cx, Cy, and Cn will range somewhere between 0.5 to 0.9 for Cx, 0.7 to 0.95 for Cy, and 0.05 to 0.20 for Cn. Okay, now you might see one particular thing, that the sway is varying as sine of gamma W, but the yaw is varying as sine of 2 times of gamma W. Why might that be the case? Why do I want to take the variation as 2 times sine of 2 times gamma W in yaw? Think about, when does this thing go to 0? When is it causing a wind force or moment to be 0? Does that make sense from what you're seeing? Yes, no? What do you think?
So even at pi by 2 angle, it will be 0.
Correct. So which means pi by 2 angle corresponds to
So 2 into pi by means the the
beam wind, right? When the wind is actually going sideways,
yes,
you won't expect to see the vessel yaw much, is what I'm saying.
yes,
It may not really be exactly be 0, but it will be close to 0 in a real typical scenario, because your superstructure might be contributing to a little bit of a moment over there.
Yes.
But more or less, you should see that the windage area should be more or less matching, so that the value of the yaw coefficient must be coming down as I come towards a perfectly beam condition. Similarly, when I come to a perfectly head-on condition or following condition wind, you should also see that the yaw moment should be kind of close to zero, which is why for a fully symmetrical ship, which means fore and aft symmetry as well as port and starboard symmetry the vessel has, then I can definitely say that the yaw must be varying as 2 times sine of gamma W, right? Because definitely in that case, a beam wind should also result in zero yaw if it's fore and aft symmetric. Right? If I make a cross section like this of my ship and it's symmetric to the fore and aft, then the windage area will be equally distributed on both sides. So I don't expect it to yaw anymore. Am I right?
Sir, but practically this fore aft symmetry will not be present.
Fore aft symmetry usually will not be present. The superstructure is typically the place where you'll have the difference.
Yes.
Right? Because typically you'll have it being wall-sided. The ship will be wall-sided after it comes out of the waterline, more or less. Right? We're not talking about the underwater geometry. We're talking about geometry above the waterline. Right?
Yes, yes, yes.
So it will be more or less wall-sided on either side. So the area will more or less match, except for the superstructure and a couple of other things on the deck. Right? So in a gross approximation, I can assume, in the lack of a better option, I may assume that it goes to zero, but in reality, it will be more like an elliptical variation. It will not be precisely zero, but the value will be small.
Yes.
Okay, so that's why we are assuming this variation to be 2 times of gamma W. That's where that thing is coming from. Okay, so now you'll see that when the ship is actually moving, so we were so far looking at what was happening when the wind speed was incident on a zero speed ship. But in typical scenarios, you'll find that the ship itself is moving and then there is a wind from some other direction. So just like as in the current case, we will be doing the same thing here too. We'll be computing the so-called relative wind velocity, which means we are looking at the relative to the ship, what is the wind velocity, and based on that, we'll be computing our drag and lift forces. Is that making sense?
Yes, sir.
Yes? Okay. All right. So similar to what we had before, you have the relative surge component and the relative sway component due to the wind specified as U minus UW and V minus VW, where UW and VW are nothing but the components of the wind taken along the longitudinal direction of the ship and the lateral direction of the ship. That is why you see that these are represented as cosine of beta W minus psi, and this is sine of beta W minus psi. We subtract those values from the existing ship's speed in order to get that so-called relative wind velocity, and then we square them, add them, take a square root of it. That gives us the total relative wind velocity. And the relative wind angle is given in a similar manner, minus of tan inverse of V by U. I think having seen what was happening with the current, this should not come as much of a surprise. You're seeing that the same thing being repeated just for the wind. Alright, in which case the total wind forcing can be written down as half rho A times VRW square times the wind coefficient times the projected area. When you are looking at the moments, you will also include the moment arm, which will be differing for all the 3 different modes as we previously discussed. Typically what will happen is we will measure VW and beta VW are measured using an anemometer and a weather vane, and this is what you see. Weather vane, is everybody familiar with what a weather vane is? Have you ever seen in an airport they have it with a cloth behind it which shows you what is the direction of the wind?
Yes, sir.
Yes, sir.
There's like a cloth piece hanging, and as the wind is blowing through, it will it will orient itself in the direction of the wind, right? So that's what is a weather vane. And then an anemometer can usually measure velocity of the wind either with respect to pressure measurements, or it can directly do velocity measurements as well. In either case, we'll be getting from the anemometer the velocity Vw. Notice that when we are computing this so-called wind forces for our application, when we measure these two quantities, the measurements must be passed through a low-pass filter before we do the computation of the wind forces. And that is because we want to compensate for the mean and the slowly varying wind forces, but we don't want to compensate for gust winds, right? Which means that a wind which is just say coming about for 30 seconds and going away. We don't want our actuators to start taking action on them immediately, because our ship's inertia is so huge. Such small high frequency wind variations will not cause a significant drift in our ship. And it's kind of pointless to get our propeller or our activations to be, our actuators to be activated in order to compensate for those forces. Right? In essence, what we are doing is we are making our actuators wear out much faster by doing that exercise. It's much better to ignore them. So which is why we will pass them through a low pass filter before we do the computation of the wind force, which we are trying to compensate. Okay, as I said, these coefficients usually can be determined experimentally or by a CFD. So when I say experimentally, they will be determined by a wind tunnel experiment or by a CFD exercise. So either way, you can find out. So that is how we will compute the so-called wind forcing vector and include it on the right-hand side of our equations of motion. All right, let's go back and talk a little bit about the currents a little bit more. Remember that when I was talking to you, we were discussing the idea that this combination MRB times V dot plus CRB times V can be expressed in a similar format, but with respect to the relative velocity vector. We'll try to see more of a proof of why that is so in this case. And it's just a mathematical formalism which I want to kind of include so that we are not getting confused at a later point. So if I assume that my total velocity vector V is nothing but VR plus VC, right? This is coming from the current, and this is the so-called relative velocity vector. Now, what I'm doing is I'm substituting this value of V in both these places. And you'll see that we get M times, and notice here that I'm only taking the rigid body mass matrix and the rigid body Coriolis matrix. I'm not talking about the added mass here. Okay? The added mass will always be with respect to the relative velocity vector because it's a fluid generated force. It will always depend on the relative velocity of the fluid. Okay, it is only the Coriolis forces and the rigid body inertia terms which are related with the V vector. We want to relate them with respect to the VR vector. Okay. Now, so I'm just substituting this expression into this two places, here and here. So you'll see MRB times VR dot plus CRB times VR plus MRB times VC dot plus CRB times VC. Our contention here is that the second term is actually equal to 0. If we can show that the second term is equal to 0, we have achieved whatever we wanted to achieve, right? We can express the mass matrix and the Coriolis terms purely in terms of relative velocity vector. Okay, Now, we know that the CRB vector matrix can be represented in a form that is independent of the linear velocity. So therefore, this can directly be expressed as in terms of the relative velocity. Tell me if this is not clear. Everybody with me on this one? We have discussed about that, yes? Yes, no?
Yes, sir.
All right. So when we come back to the second part, we need to show that the second part is actually equal to 0. And it is actually easy to see if we expand out this mass matrix and the Coriolis matrix, it is easy to see that those two terms add up to 0. So I'm only looking at this portion here, okay, and I'm expanding that out. I have the mass matrix, which is given by here, and then I have the, okay, there's a mistake here. This should be VC dot. Yeah. And that VC dot is given by here. Now you might ask, why is that I'm not actually seeing a current velocities derivative, but I'm seeing some skew symmetric matrix and something multiplied by VC. How did that come into the picture? I'm going to talk about that in just a minute, but bear with me here and assume that this is equal to VCB dot. So which means that I'm taking the current velocity expressed in the body fixed frame and I'm taking a derivative of it, and that derivative is given by the skew symmetric matrix times this. That is coming because the current does not vary in the inertial frame. Okay, typically what happens if I express this current velocity in the inertial frame and I take a derivative, that thing must be equal to 0, but not necessarily in the body fixed frame. Okay, so that is what is happening. Actually, let me finish that and then come back here. So if I see what is the current velocity in the NED frame, that is nothing but a rotation matrix multiplied by the current velocity in the body fixed frame. If I take a derivative of this, I'll get this, right? I'm applying chain rule. Derivative of R times VC plus R times VC dot. But if the current is irrotational, then this must be 0. In the NED frame, the current is not changing a direction. It's keeping its direction. Everybody with me here? Yes, Anand?
Yes, sir.
All right. So from this expression that this is equal to 0, I can see that VCB dot can be expressed as minus R transpose R dot times VCB. Everybody with me here?
Yes, sir.
Now, we know that this R dot is nothing but R times S of omega n B. We have seen that before, that the derivative of the rotation matrix actually can be related to the rotation matrix times the skew symmetric matrix with respect to the omega. So that is where that skew symmetric matrix omega is coming into the picture. And since this R transpose times R is unity, or that is the identity matrix, what we are left with is this. So that is why in this expression, instead of VCB dot, I am putting minus omega NB times VCB. Is that making sense now? How we got that?
Yes, sir.
Yes, sir.
Okay. Now, the second matrix, the Coriolis matrix, I just keep it as is, and we are taking a representation of that representation where it does not depend on the linear velocity. I'm just bringing that in and putting that here. Now observe, if I just take the first sub row of this thing and I multiply it out, what do I get?
M into S omega n B, B into VCB.
And in the second term,
That is 0.
no, I get that here as well, right? M times
Yeah.
times VCB, I'll get plus M times S omega NB times VCB minus, I'll get here. So when I add the two, I should get 0.
Yes.
Right? What happens in the bottom sub row?
It will be M into S R B. It will be the same, I think.
It will
The
be the
both
same,
terms,
right?
both
Because
terms will be present.
correct, this term and this term will be multiplied, and then this term and this term will be multiplied, and both of them are the same but opposite sign, so they'll cancel out, yielding me a 0.
Yes.
Okay, what is that telling me? It is telling me that this thing, MRB times VC dot plus CRB times VC is 0. Correct?
Yes.
Yes, sir.
So that means now I can express everything in terms of the relative velocity vector, and I have kind of shown that it is an equality. Whether I write MRB times V dot plus CRB times V, I can also write it similarly as equal to MRB times VR dot plus CRB times VR. Both are equivalent expressions. That's what we have shown here. So rather than just having a discussion in words, what we had previously, we've kind of formally proven that mathematically that should be the case here. Okay, that's just for completion. Okay, so in any case, we have seen this one before, so I'm not going to spend too much time on this. The state space model for the relative velocity case, when the currents are also included, we have seen that it can be expressed as this, where we have all the terms again taken to the right hand side so that it can be expressed in that so-called state space form, which we can use to simulate the dynamics. Okay. Similarly, we are also seeing that if you wanted to write it in terms of absolute velocity vector, we'll need to bring out the additional component due to the current. That extra term will come out and sit there. We had seen both these in the previous classes. We've seen this exact same modeling, just including here for completion. And we also saw that in case of a 3 degree of freedom horizontal plane motion, this gets simplified a little bit as shown here, which also we had discussed in our maneuvering model. Only note that here instead of the J matrix, we now have the rotation matrix depending purely on the sign, because we are only looking at a 3 degree of freedom system. Okay, now let's cap it all off by giving a short discussion about how to model these wave responses. So we talked about the wind, we talked about the current. What we did not talk about so far is the wave. Now, a typical computation of wave, you already know. You all are already aware because you either had it in your statics and dynamics course or the undergraduates had it in their ship motions course. Right? So given a particular sea state, how do I compute the motions? What is the typical process?
Like with RAO, we know the unit amplitude or at versus height, like per height. So at any given sea state, we know the heights, so we get the responses.
No, suppose I just told you, find me the response of the vessel in a Pearson-Moskowitz spectrum. How would you go about it? Where would we start? How do we go about it?
So like that spectrum is consisted of different omegas.
Mm-hmm.
So we know the we can divide it into different frequency components waves,
Mm-hmm.
and take the like effect of each of those components, like different frequency components on the ship.
So individually, I break the wave elevation into regular wave elevations of regular waves. Right? I evaluate the response for each regular wave using RAOs that I know for the vessel, and then I add them all up to get the total irregular response in the of the vessel in the irregular sea.
Yes.
Right? That is the principle of superposition.
Hmm.
Right? But this is valid only when we are the first order wave forces I'm considering. If I'm considering second order wave forces like the ones which we discussed in one of the classes previously, then you need to incorporate them separately. Those second order wave forces also need to be incorporated. Now, calculating that second order wave forces is quite a challenging topic. Okay, you usually require the what you call a precise definition of the hull form, and then you have to feed it into a program like WAMIT or Hydra, and then they have to go through the process and compute what is called as a quadratic transfer function, which then gives you the so-called mean drift forces. So it's a pretty involved process. So from a control standpoint, when we want to test out our controller for simulating and testing whether how well it performs, we may not be interested in doing a precise modeling of the waves in the traditional manner. We want something simpler. We want something which is robust enough, but somewhat represents the reality, but need not represent the reality in an exact manner. So what we are going to talk today about is how can I look at a wave elevation's effect on the hull can be modeled using some simpler models where I'm making some gross approximation, but nevertheless it works out well for testing and simulating purposes. Okay, the idea here is that instead of computing the RAOs from a potential theory program like a Hydra or WAMIT, we can represent these RAOs using what are called transfer functions, which are coming from the Laplace domain. And we have seen this before. It's a simple second order differential equation for which I'm giving some input and I'm getting some output. That transfer function is what I want to tune so that it represents the so-called wave motion. Okay, so in this set, the input to the system will not be the wave elevation, but rather I'm just giving Gaussian white noise, like random white noise is the input which I provide to my system. But I want that output of that system to be somewhat representative of each of the 6 degrees of freedom. Okay, so I'll have 6 different second order systems where each one will be representing one for each mode. So one second order system will transform a Gaussian input noise, white noise, into a, let's say, surge. The next one will transform it into sway motion. The third one will transform it into heave motion, so on and so forth. Okay, this does not represent reality. Let us be very clear. Okay, if you really wanted to represent the reality, you need to know whatever you did in your statics and dynamics or ship motions course. You have to find the RAO properly and then figure out what is the motion for the given wave elevation from a spectrum. But here I am kind of taking a shortcut because my objective is to have a representative signal which looks like it, but I'm not really interested in getting it exactly right because my objective here is to test whether my control system can deal with signals which are looking like that rather than exactly seeing how it deals. It's for testing purposes. Is everybody understanding what I'm trying to say?
Yes, sir.
Yes.
Yes, Aditya?
Yes, sir.
Yes, okay, good. So the idea here is that we want a representative system where each of the modes, so as I goes from 1 to 6, I have the surge, sway, heave, roll, pitch, and finally yaw. For each of them, I'll have a system like this where I have this so if I wanted to write down the corresponding differential equation for this, can you write down the corresponding differential equation for this transfer function which you are seeing here? What will it look like? What do we have?
Like d square eta by dt square plus 2 lambda omega e d eta by dt plus omega e eta is equal to that k omega omega k kwi omega k
K,
omega omega but
KW.
that in d d d omega by dt, that right
Mhm.
side.
Correct. So we have eta double dot plus 2 lambda omega e times eta w dot plus omega e square eta wi is equal to wi times wi dot of, this is the corresponding differential equation. So I'm taking the white noise and its derivative, and I'm feeding that derivative as an input to my second order system, and out comes my motion. Okay, what can I tune here? I'm actually tuning this value of kwi. That is what I'm tuning. Okay. I can tune my kwi so that my transfer function starts to look or give an output which looks similar to what I would get from a typical ship response. It won't exactly match, but it's a start. Okay. Notice that omega e here represents the encounter wave frequency. So depending on which wave I am getting, I am looking at that encounter wave frequency, and for that I am computing the so-called response. Okay. All right. Then so in this case, the 6 linear state space models for the wave elevation response can be written as xwi dot is equal to some matrix awi times xwi plus some matrix e times wi, and the output of the system is nothing but the modes that I'm looking at: surge, sway, heave, roll, pitch, and yaw. Okay, and that is given by some matrix C multiplied by the state vector X. So in order to kind of make sense of this, let me try to put this in perspective together. So if I expand and look at what is that A matrix, it will simply be 0, 1 minus omega e square minus 2 lambda omega e. Yes, everybody with me? Second order system, so it should have 2 states, and that is the 2 states that I am considering. And my output is only one of those 2 states which I am actually tracking. So instead of the e velocity, I am monitoring the e displacement. I am discarding the velocity by putting 0 here. Everybody with me so far? Okay. All right. We'll try to have an assignment on this and the modeling together so that we can kind of appreciate what is going on here. I'll try to put that up by next week. We'll try to see something happen there in MATLAB Grid. Okay, notice that this only models the first order wave induced motions, and it does not really take into account the second order wave drift forces, which are also important for us, especially when we are looking at the controller, especially when you are looking at the integral action of your controller. You'll later on find out that in your PID controller, the I component is really important for accounting for steady state errors to be minimized to 0. Right? Which are slowly varying forces should be accounted for in some sense. So in that case, the second order drift forces, which are slowly varying or are mean values, will be important to be modeled. And therefore, those have to be modeled also in some sense in an approximate manner. What we do therefore is we try to combine everything together into a so-called composite model, where we have one model for the low frequency, one model for the wave frequency, which we just discussed, and we'll also have a component, another model for the second order drift forces, to model them in a slowly varying manner. So let's look at what that model is. So the low frequency model is the one which we are already familiar with. These are the maneuvering model which we talked about in our classes. Okay. The only difference here is that the wave drift forces which we see here, they are included here, but the first order wave forces are not included. So previously we simply had the forcing due to the waves, but I have now kind of separated it out and said that I'm looking at slowly varying wave forces only. I do not want to account for the fastly varying wave forces because I can actually compute the motion directly using the model which we just discussed, which is that wave frequency model. Right? So this fellow is directly giving me first order motion. So I need not include that eta into this eta. I can reserve this eta purely for low frequency stuff. Is everybody following me? This is where everything is getting united. So please pay little attention here. This is where all of our modeling, whatever we have discussed so far, ties up into a single model, which we'll later on be using further. Alright, so since I have already included the first order motions, I'm only including the low frequency motions into my eta here. And similarly, all the dynamics is now only governed by the slowly varying stuff in the low frequency model. Now, one might wonder, what do I do about these drift forces? I do need them, how do I compute them? And the third thing which we will look at is the wave drift model. And what we are doing is we are giving a Gaussian white noise as an input to a system and then integrating that Gaussian white noise in order to so-called get our wave forces. Again, here what I am doing is I am taking a Gaussian white noise is a fastly varying process. I am integrating over it so that it becomes relatively slowly varying, and I can again tune how fast the noise is varying, how much is the standard deviation of the noise. These are parameters in my hand that I can tune so that what I get as an output represents somewhat relative to what a second order wave force would look like on the model. Okay. Notice that this is not an exact model as we were doing with the first order wave forces as well, but it helps us get started on tuning our controller much faster than actually developing this accurate model for the dynamics. Okay, as long as we are able to deal with signals in the same frequency regime, whether it is artificially generated or really experienced by the ship, we will be able to account for both of them using the same controller. That is the main idea. Okay, so what we are doing is we are taking a so-called white noise whose parameters we can tune, and then we are integrating over it in order to get the so-called second order mean drift forces. And finally, our total measurement is now going to be that slowly varying low frequency stuff plus the first order wave frequency stuff plus the noise. Okay, this noise is coming into the picture when we are using any measurements. So if we are trying to use like an IMU or a GPS sensor to do these measurements of X, Y, and psi, then we must include that noise because it will add a considerable amount of noise to the measurements, and that must be included in our model. So if I want to look at the block diagram of this, what is happening is I'm feeding white noise into this box, the top box, and which is kind of assuming that a linear wave spectrum approximation, assuming that the white noise is what is driving my system. It gives me the output as the first order wave motions. The control inputs, which are our propulsion and the rudder, they are now governing our slowly varying dynamics. So I'm getting the slowly varying eta, or the position and the heading angle. From that, I add the two together, and this is what I usually measure from my sensors. And that's why you generally see a noise added to it. Notice that here this noise vector as well as that 0 WD, which is the white noise driving the wave drift forces, are zero mean Gaussian white noise processes. Now, this is not a course on stochastics, but we will kind of see how to simulate these processes in MATLAB assignments. But I won't be delving more into the mathematics of what is a Gaussian stochastic process and all those things. They're not relevant for us. I mean, from a standpoint of practically applying these concepts, we don't need to know that, but it is always great to have an understanding about it. So those who are interested can try to pick up more on it. But for our class purposes, we'll only restrict ourselves to how to do it using MATLAB rather than bothering more about what is underlying, what is the stochastic process, what is its definitions. Those things will not be spending our time. So this is that so-called unified model which we are looking at, where we have the low frequency model, wave frequency model, modeling of the wave drift forces, and we are measuring the output, which is combining the low frequency and the high frequency stuff. Okay, so whenever we want to design our controller, since we want to exclude that high frequency stuff or the wave frequency stuff, we might want to take our measurements Y and pass them through a filter so that the high pass, we are doing a low pass filter so that the wave frequencies are eliminated and we get the so-called low frequency signal out. And we design our control actions based on that low frequency stuff. Okay. More on that we will talk when we discuss about navigation. Okay, but for now we will presume that this is our total modeling based on which we will be designing the controllers and the navigation modules. Okay, so that brings us to a completion of our modeling section of the vehicle. So we now have a good enough model that we can now start discussing about guidance, navigation, and control. From the next class onwards, we will start on discussing the controller aspects first, then come back to the navigation, and then come back to the guidance. That is, in that order, we'll try to attack it. Okay, any questions so far?
So the white noise thing will be like completely totally random thing, right? Like
Correct. So typically when we say it is a white noise, what I mean is that it is its autocorrelation function usually looks like a delta function. Let me specify what I mean. So let's see. So if I take a signal and I shift it by some time, okay, so the same signal, it's shifted by a certain time. You get the idea, right? And now I'm kind of multiplying it with itself. So I'm taking, let's say that is eta of t times eta of t minus tau. Okay, and I take an average over all time. Okay, which means I'm integrating this quantity over the entire time t. Then what we get out here is called as the autocorrelation function R tau. And typically for a signal which has some frequency components, you will see that it will be a symmetric function on either side. And it will look something like this, and it will kind of die down over time. Okay, but when I'm dealing with a what you call white noise, what it means is that the very next step, it is uncorrelated with the previous step. So in this case, the autocorrelation function simply becomes like a peak. Okay? It means it's simply non-zero only at this point, and it's zero everywhere else. Okay, which means it's like a Dirac delta function. Everybody knows what a Dirac delta function is? You've seen this before, right?
yes, sir.
Vibration scores.
Yes. So like the signal, the white noise will be like itself only at the zero, like tau is equal to zero.
No, no, no. What it is meaning is, this is not meaning that the signal will be zero at every time.
No,
What?
no, like it will be like itself. Like you are saying the autocorrelation, right?
Yeah, it will be correlated to itself only at that time step. At the very next time step, it can be anywhere,
Hmm.
right? It is very hard to imagine such a process. In a
Yes.
physical process, you will not see that happen. But this is a limiting phenomenon when I say it's a white noise, because the very next time step, in a physical process, it can't happen. So suppose I'm looking at roll motion of a ship, let us say. At one point in time, I have 35 degrees of roll. At the very next instant, I can't have minus 40 degrees of roll. You and I know that because the ship has inertia, so therefore it will slowly respond, so therefore it's going to move slowly. It's going to move from minus 30, from 35 it may go to 32, or it may go to 37, but it can't go to minus 35 suddenly, right? So whereas in a unphysical process, this is a gross approximation. So when I say it's a white noise, it means that it is really not related to itself at the very next time step. Now, if you look at the so-called spectrum of this process, the spectrum is nothing but the Fourier transform of this R of tau. That is the spectrum of the process. And the spectrum of the process will be flat. That is why the white noise. Okay, which
Or
means that
also,
every frequency is having equal energy when I am looking at the distribution. Is that making sense? So
yes,
no
sir.
matter what frequency I choose, the energy is equal at every frequency. Now one might wonder, sir, if this is the case, when I actually try to compute the variance of this process, it should be infinity, because the area under the spectrum is infinite in this case, right? So technically, yes. Technically, theoretically, for a white noise process, it is very difficult to define things like variance. Although you can define variance in a what you call, if it is a mathematical way to describe it, you can get it out as a variance value, you can get it out. But usually these processes are not physical. So what it is saying is, let's say that if I look at the process physically, at some point I'm here, let's say, at the next time instant, my process could continue like this, or it could continue like this, or it could continue like this, or it could go somewhere. It can go anywhere, and I don't know where it may go, which is why it's not a physical process. Okay? But it is a very good approximation, because white noise is very easy to simulate. It is very simple to bring about, and you'll kind of see that in the assignments how to simulate that white noise for our purposes. It's very simple. We have to take a spectrum which is flat, discretize it, and get the values out and be able to get it. Now, the farther you increase your omega values up till which you are choosing, the Nyquist frequency becomes larger and larger, the more variation you'll see in your process. Okay. So this white noise approximation is useful in that sense. It's not a physical process, but it is useful for simulating these sort of things. And because it is Gaussian in nature, and it has simple properties that we need to only know its standard deviation and mean value. Mean is 0 in this case, right? So it allows us for these processes can be fully characterized. We know everything about the process because it is a Gaussian process. The moment it is no longer flat, we call that a colored noise. So if you look at wave spectrum, you can think of a wave spectrum as an example of a so-called colored noise, because not every frequency has the same energy level anymore. Okay? And I'm really going out of syllabus here. This is really not part of this course. Okay. So just understand that the white noise process approximation helps us simulate stuff easily and to see what is going on rather than actually creating an exact model. So it's much easier to go past this. Okay, all right. Any other queries? Let me stop recording in that case.